Okay guys, in this video I'm just going to try to do out a bunch of sample problems. I'm just going to kind of make up problems on the fly here and solve them. As I've said to you all before, I think the best way to learn about Newton's second law is to just do lots of problems. The more problems the better, and eventually you kind of get the hang of it. And as you get the hang of it, I think start to understand some of the underlying theory a little bit better as well. So I could do tons of problems. I'm going to try to do maybe 3 or 4 in this video, different types of problems. So let's start, maybe this is kind of a classic setup. Let's imagine I've got the following situation. I'm going to imagine I have a tabletop and I've got a pulley and I've got 2 blocks. I have a block here connected by a rope to a hanging block here. And maybe we'll say that this is a frictionless surface, and we'll give some masses. I'll call this M1, and that will have a mass of, we'll say 2 kilograms, and this will be M2, and we'll say it has a mass of 4 kilograms. And we're going to say, let's imagine it starts from rest. We're going to imagine that the mu is 0, there's no friction. And maybe just for simplicity's sake, if you'll allow me, I'm just going to call G10 meters per second squared, just to make the math a little bit easier. And I'm going to ask 2 questions based on this. I'm going to ask, what's the acceleration of M1? And then I'm going to ask, what's the tension in the rope? So if I want to know the acceleration of M1, this is, I've done a problem like this. I'm realizing similar to this, and that it's a little bit tricky because you might be tempted to think of your system as M1. So just to remember the 3 steps, right? We have to choose our system, then we do the FBD, and then we do F equals MA. Those are our 3 steps. So the system, you might think to choose M1, but this is one of those cases where since M1 cannot accelerate without M2 also accelerating, we need to use for our system the 2 blocks together. And if I think about the forces that act on that system, the forces that act on the 2 block system, I've got M1G here. So I've got this mg, which is 20. I've got mg here, which is 40. I've got a normal force here, which is also 40. These 2 have to be equal because M2 doesn't accelerate vertically. And those are the only external forces on that system. Since I've chosen for my systems both blocks taken together as my system, that means that I don't draw any of the internal forces related to tension or anything like that. So now let's go ahead and solve. So my F net equals MA. Remember, there's no friction here, so the net force, since these cancel, the net force is simply 20. So I'm going to say 20 equals MA. Since my system is both blocks, I have to take the combined mass, which is 6, times A. So A is whatever, 10 over 3. 3 1/3 meters per second squared. That's the acceleration of the system. Now, if we want to go ahead and think about the tension force, here's where we have to change the system. When I chose as my system this 2 block setup, when that was my system here, the tension force was internal to that system, so it doesn't appear in my FBD. And so I need to choose a new system. So now I have to choose just 1 block or the other. It doesn't matter which one we choose, but I'm going to choose maybe just think about M2. And if I only think about M2, then there's another force in my force diagram. We've got mg and the normal force, which cancel as we noted before. But now there is this tension force as well. There's also now a tension force this way on M2. Now we note, again, that tension force also acts upward on M1. And these 2 tension forces must be equal. As I've noted before, the tension force in the rope has to be the same everywhere in the rope. Otherwise, the different ends of the rope would have different accelerations and the rope wouldn't be a single piece of rope. It would be a broken rope. So now I've chosen a system that will work. I've chosen, again, just M2 as my system. I've drawn the FBD. And now I see the tension force is the net force on the system. Since these forces cancel, again, I know that the tension force is the net force. And so now I'm going to say the tension force is equal to MA, but now it's just M2. It's not both masses. Since I changed my system to M2, it's just the mass of M2 that I'm considering here. So that means that the tension force is going to be equal to 40 over 3, or whatever, 13 and a third meters per second squared. Newtons. Newtons, that would be the tension force. That also, again, would have to be the tension force here. All right, so that's one problem. I like that because you have to be careful about your system. We could try a friction problem. Let's imagine the following. Let's imagine, we could do a lot with this kind of problem, but let's imagine I've got a ramp, and I'm going to say that the angle of the ramp here is 30 degrees, and I have a block that is at the bottom of the ramp, and it's moving upward. It begins moving upward with an initial velocity of, well, it doesn't matter actually, well, but I could just give it a speed, but we're not going to use it. 10 meters per second, and we'll say that it has a mass of 5 kilograms, and again, I'm going to use G equals 10 just for simplicity's sake. And I'm going to give you some mu values. I'm going to say that mu sub S is 0.6 and mu sub K is 0.2. Okay. And now what am I going to ask? I am going to ask on the way up, I want you to find the acceleration of the block on the way up the ramp. So the block's going up the ramp, what will be the acceleration? So here I don't think finding the system's hard. We know what the system is. The system is just the block. There's only one object here, so it's not a particularly tricky situation to choose the system. So if that dot represents the block, what are the forces? I know I've got gravity acting downward like this. That's mg, which is 5 times 10 or 50 newtons. I've got the normal force, which is acting this way. And then I have a friction force. Now, since it's moving, I think it's pretty clear we're going to use the kinetic friction model. What's the direction of the friction force? Well, remember that the friction force will always oppose the motion. And since the velocity is up the ramp, that means that the friction force, the kinetic friction force, is down the ramp. So that's going to be my free body diagram. Now, if I want to use F net equals ma, what I'm going to do is I have to go ahead now and split mg into components. I have to find the components of mg. I have a component acting this way. We sometimes call that the y component. So that's going to be, then I have what I sometimes call the x component, the component parallel to the ramp. So here are the two components of mg. We remember that if this angle here is 30 degrees, then in my picture here, this angle is also 30 degrees. Meaning this component here is going to be equal to 50 cosine 30, and this component here is going to be equal to 50 sine 30. I don't have a calculator handy, so I'm not going to be able to give you precise values, but this is going to be something like 43-ish newtons, and this will be 25 newtons, that I can tell you. So now I've got the components. Why does that help me? Well, first of all, when I go ahead and write my F net equation, I know that these two forces in my picture, these two are going to be equal. So they're going to cancel, which means the only forces that are going to contribute to the net force now are this right here and this right here, the two forces that aren't canceled, and they are additive. The friction force and this component, this what I call the x component of mg, are both acting down the ramp. So they're additively contributing to the net force. So I know that 25 is going to go into the net force calculation. To find the friction force, I need to know the normal force, which is 43. I just said that these two forces have to be equal. So if we go back to this now, I say that the normal force is also 43 newtons, which means that the force of kinetic friction, which is mu times the normal force, is 0.2 times 43, right? Which is going to be 8.6 newtons, or roughly thereabouts. All right, so I've done all that hard work, and now I'm ready to finish this by doing the F net equals MA calculation. So here I go. F net equals MA. I've got two forces that are both in the same direction down the ramp. That's 25 plus 8.6. 25 plus 8.6 equals 5A. And I'll remind you that some of you might have been thinking to yourself, oh, but I want to make down the ramp negative. I just always make these values positive. And I always, again, if I'm subtracting, I do bigger minus smaller so that I know the magnitude of the acceleration. If I want to know the direction of the acceleration, I can figure that out after the fact. It's always going to be in the same direction as the net force. All right, so this gives me 33.6 equals 5A. Which means A is going to be something on the order of 6.7-ish meters per second squared. You can figure out the exact values on your own if you have a calculator handy. All right. Okay. How about this? Maybe I could now ask, so what's going to happen? What does this mean? It's accelerating. What's the direction of that acceleration? Just to be clear here, the direction of the acceleration now is this way. It is going down the ramp. How is it possible that the velocity's up the ramp, right? This is the velocity up the ramp, but the acceleration's down. Well, that just means it's slowing down, which makes sense. If I were to, shoot this block up the ramp, it's going to slow down, and eventually it's going to stop. Now, why is that interesting? Because when it stops, that means we're going to be in a static friction mode. And there is a possibility that when it stops, and we're now in a static friction situation, since the static friction is greater than the kinetic friction, there's a chance it's going to stop and not come back down the ramp. So I could ask myself, or one way I could express this is, what's going to be the acceleration down the ramp? So I'll write this up here, A down the ramp. And it could be 0. It might be that the block will just stay there. And we'll see that. So let's imagine now, it might be 0, it might not be, but let's go ahead and draw a free body diagram of the block when it's at the very, very top. So this is at the top. Here's the block. Okay, we've got mg acting straight down again. Maybe I'll zoom in on this so I don't take up too much space. So that's the block at the top. We've got mg acting straight down. We've got the normal force acting this way. At the very, very top, when it stops, what's the direction of the friction force? Well, now the friction force is going to change directions, and it's going to be up the ramp. And it's going to be up the ramp because when the block stopped at the top of the ramp, its tendency, if there were no friction, it would start to move down the ramp. And friction, again, will always oppose the tendency of the object to move. So since the block wants to go down the ramp, friction now is going to be up the ramp. So what we have to do, remember, we've done problems like this, is we have to test. The first thing that we have to do is test, or I'll say this. The first thing I'm going to do is test static friction force, Fs max. Will the block move? And to do that, if I zip back onto this, the way I'm going to determine that is by, again, splitting up the mg into components. We've already done that. We did that over here. We had, if you'll remember, 43 was this component, and we had 25 as that component. So I'm going to use those same values, 43 and 25. And if we now look at the static friction force, I'm going to see what Fs max is. Fs max is going to be 0.6 times 43. That's mu s, which is 0.6, times the normal force, which is 43. So the normal force is 43, Fs max is 0.6. And what is this? Oh, well, that's actually going to be really close. That's going to be, what, 25.6, I think, newtons. So what does that mean? Well, that's actually interesting. I wasn't intending this, but that means it's not going to move, right? 25.6 is a little bit more than 25. So the force now up the ramp, holding it up, is more than the force down the ramp. Now, we have to be very, very careful here. I've said this before. When I calculate Fs max, remember that the static friction force is less than or equal to 0.6, or I'll just write it in symbols, mu s times the normal force. In this case, it's going to be, the static friction force here is going to be less than 25.6. It would not make sense at this point, at the very, very tip top, when the velocity is 0, it would not make sense to have a net force up the ramp. That would imply that the object is accelerating up the ramp due to friction. And friction would never cause an object that's not moving to start accelerating. So actually what we can say, I'm going to go ahead and just amend this by just remembering that this, if I can get rid of it, it will let me. There we go. The Fs is less than or equal to this. And so what do we note here? Well, we note that since the maximum value of static friction is more than 25, the static friction force will simply match the force down the ramp. And so the acceleration here, it will not move. So we answered no, which means the acceleration is 0. And I'll just remind us then, so what is the, maybe I'll ask the question, what's Fs at the top? And it is, Fs is exactly 25 newtons. It will not be 25.6. That is just the maximum value. Conscious that this video is getting long quickly. Maybe I'll just do one more. There's so many different types of interesting problems we can do. This is a classic one, though, and it won't take too long. We imagine here that there's a situation, it's a weird setup, but we imagine that there's a situation where we have a person standing on a scale in an elevator. I think we had a homework problem like this. But it's sort of an interesting kind of classic type of problem. So let's imagine that this person has a mass of, we'll say, 60 kilograms. Again, I'm going to use G equals 10. And what I'm going to say is that this elevator is accelerating upwards at 2 meters per second squared. So maybe the person's gotten in the elevator at the lobby floor of the hotel, and they hit the button for the 5th floor, and the doors close, and the thing starts to accelerate upwards. Now, what we ask here is, what will the scale read? The question is, what will the scale read? I'm sure none of you have been on a scale in an elevator, but you could try this. It would be sort of interesting. Bring your bathroom scale with you next time you go to a hotel. And the first thing you might think to yourself is, well, why the hell would the scale read anything different from what it usually reads, which you think is your weight? And that's because the scale does not read your weight. The scale knows nothing about your weight. The only thing the scale knows is how hard it pushes up on you. I'll say that again. The scale reads the force that it pushes up on you. Now, the force it pushes up on you is, of course, the normal force. So a scale reads the normal force, not your weight. Now, it turns out that there are certain circumstances in which the normal force is equal to your weight. If you are standing in equilibrium on the bathroom scale in your bathroom, you're not accelerating. And if A is 0, I'll make a note of this. If A is 0, then the normal force, F sub n, is equal to your weight. which is why if you go in the bathroom scale and you just kind of stand there very still, you can trust that the bathroom scale reads your weight. If, of course, you start jumping up and down on the bathroom scale, you'll see that the scale reading fluctuates. Your weight isn't fluctuating, but since the acceleration is not zero, that would be a situation where the normal force reading of the scale is not matching your weight. Okay, so what will the scale read? Well, with that introduction that the scale reads the normal force, what I'm going to do, I know what the object in consideration is. It's the person. Here are the forces. I'm going to do the FBD. We've got mg down, which is 60 times 10, or 600 newtons. We've got a normal force up, F sub n. Since the acceleration is up, since the direction of the acceleration is up, that means the direction of the net force has to be up as well. So now when I go ahead and write an F net equals ma equation, this is step 3 in our 3-step process, the net force, I know that F sub n has to be bigger than mg because the direction of the net force is up. So the up force has to be bigger than the down force. So that means I'm going to write this as F sub n minus 600. Again, bigger minus smaller has to equal 60 times A. And I know that the A is 2, so maybe I'll just go ahead and write that the A is 2 right here. So that then tells me F sub n equals 600 plus 60 times 2, which is 120. So the normal force then is just 720 newtons. Fairly straightforward calculation once you figure this out, but I think this sometimes is confusing, this business of the scale reading the normal force. So that was probably worthwhile. Hope these were helpful. If they are, maybe I can do more of them.